All right, so we now want to talk about polar coordinates. Polar coordinates is appendix, it's in the appendix sections H.1 and H.2. And the idea is that rectangular coordinates, X, Y coordinates, you've used all your life. But sometimes a different coordinate system is useful. And the polar coordinate system is very useful, particularly when you have a circular. Well, you'll see what I mean, but it's good with circles, okay, and trig functions and so forth. So let me go ahead here. So at the bottom of your ebook, there's a thing for appendices, and that's what I'm going to click on here. I'm going to click on appendices. And I'm going to find Appendix H, polar coordinates. Okay, and we're here. So right away, it mentions that polar coordinates offer, we're in section H.1, polar coordinates offer an alternative way of locating points in a plane. They are useful because for certain types of regions and curves, polar coordinates provide very simple descriptions and equations. The principal application of this idea occurs in multivariable calculus, that's Math 280, which actually I'm teaching in the spring. It can be used for evaluation of what are called double integrals and derivation of Kepler's laws of planetary motion. So, but let's just sort of, folks, stay on point here. Let's look at some examples. So I go down here, figure 1. So you see there a origin, and you see, hold on. Yeah, you see an origin in figure 1. You see the polar axis, the x-axis. You see an angle theta, and then a radius r drawn out from theta to some point P. The point P has polar coordinates r and theta. R is a radius, and theta is an angle measured from the positive x-axis. Okay, so if you have a angle and a radius, you can identify a point in the xy plane. Okay, now I'll mention this right away. Let me go to the whiteboard. Let me mention this. Right. So I'm going to draw here. I'm going to go ahead and draw. Well, I'm going to try. I'll just do it, I guess, freehand. That's fine. One moment. Okay, so I have my two axes, and let's say that I have a point P here, and my angle theta is pi over 4, and let's say my radius is 2, r equals 2. The polar coordinates are given in the order of r and theta. So r is 2, theta is pi over 4. So do you agree that if we have an angle, usually we do the angle first. We draw the angle, and then we move out a radius r. Then we locate a point in the xy plane. Give me a thumbs up if you're okay so far with that idea. Okay, wonderful, wonderful. Well, now polar coordinates are not unique. Polar coordinates are not unique because you see, we could have, for instance, a theta like this. Okay, maybe I'll draw it a little bit nicer there. So this theta would equal pi over 4 plus another 360 degrees. Okay, and 360 degrees is 2 pi. 2 pi is 8 pi over 4. That gives you 9 pi over 4. So another possible polar coordinate for point P is 2, 9 pi over 4. So polar coordinates identify a point in the xy plane, but unlike rectangular coordinates, they're not unique. You can have an infinite number of polar coordinates for any point in the xy plane. Yes, Clea?
I just wanted to ask how we get 8 pi over 4, but I get it now.
Okay, all right. Very good, very good. So, okay, so in example 1 in the ebook, they graph some polar coordinates. So let me go to the ebook here. Let me go to the ebook. Okay, so in example 1, they want you to plot the points whose polar coordinates are given. And they have 5 polar coordinates there. So the first polar coordinate is 1, 5 pi over 4. Well, 5 pi over 4 is 45 degrees. So 5 times 45 degrees is 225 degrees. So in figure 3, they graph the polar coordinate 1, 5 pi over 4. For B, the polar coordinate 2 pi over 3, well, they graph that in the second picture. So pi is 180 degrees. So 3 pi would be 540 degrees. And then so you move out a positive radius 2. So when you move out the positive radius, you move forward. You move forward. So that's why figure 3 is as you see it, the polar coordinate. For C, the polar coordinate negative 2 pi over 3. Well, negative 2 pi over 3 is a negative angle. So as you learned in trigonometry, negative angles, you don't go counterclockwise, you move clockwise. So you move clockwise 120 degrees, and then go forward a radius 2. And then finally for D, you have the polar coordinate negative 3, 3 pi over 4. So polar coordinates, actually the radius can be negative. So interesting, but there you're allowed to have a negative radius. So in the fourth picture there, what they do is they go out, well, normally you draw the angle first. So 3 times pi over 4, that's 3 times 45 degrees. So in the fourth picture from the positive x-axis, you go counterclockwise 135 degrees. But then you don't move forward 3 units, you move backwards 3 units. And so the coordinate negative 3, 3 pi over 4, that polar coordinate, that is located in the fourth quadrant. So those are examples of how you would graph some polar coordinates. And in your web-assigned homework for H.1, they have it's usually multiple choice. They'll say, all right, which graph below is for this polar coordinate? And you have to do the matching. Okay. Are there any questions so far? All right, I'm just looking through things here a little bit. All right, so let us continue. Let us continue. The book has very good examples. So now you learned in trigonometry that you can relate. Well, you remember, hold on. Is it not? Hold on, this should be moving. Oh wait, hold on. Okay, yeah, that's what I want. So the cosine of theta, as you know, is x divided by r. The sine of theta is y divided by r. So that means x equals r cosine theta and y equals r sine theta. And so if you're presented with a polar coordinate, you can find the Cartesian coordinate, or I should say the rectangular coordinate, simply by using the fact that x equals r cosine theta and y equals r times the sine of theta. Okay, so hopefully this shouldn't be a surprise. Some of the problems in the book you convert from polar coordinates to rectangular coordinates, okay, or Cartesian coordinates. So also another couple key formulas that are important, and you know this from your trig days, is that r squared, the radius, equals x squared plus y squared. The tangent of theta is y over x. Okay, so for example, if you wanted to convert, the point 2 pi over 3 from polar to Cartesian coordinates, well, x equals r cosine theta and y equals r sine theta. So x would be 1 and y would be root 3. Therefore, in Cartesian coordinates, that polar coordinate has Cartesian coordinates 1 and root 3. Okay, you see how that works? Are there any questions on that? All right, well, let's look at example 3. These are pretty straightforward examples. In example 3, they want you to represent the point with Cartesian coordinates, 1, negative 1, in terms of polar coordinates. Well, 1, negative 1 lies in the fourth quadrant, and the reference angle is 45 degrees. Okay, so the polar coordinates, well, they give several, but let me see here. Yeah, I mean that's easy enough to do in the blackboard. I can do that example 3 in the blackboard, not a problem. Whoops, hold on. Okay, so for our picture here, here's x, here's y. And 1, negative 1 we know is there. And we can construct a right triangle, right? A right triangle. So the distances, this has a distance of 1, that leg. This leg has a distance of 1. And that tells you that your reference angle is pi over 4. Okay? So the Cartesian coordinates are 1, negative 1. What are the polar coordinates, r theta? Well, of course, the radius has to be square root of 2 because, 1 squared plus 1 squared equals r squared. I'm sorry, I should say 1 squared plus negative 1 squared. Equals r squared. That's that x squared plus y squared equals r squared. So 2 equals r squared, root 2 equals r. So the radius is root 2. And, well, theta, you could use this as theta. That's 7 pi over 4. That's one of the possible angles. 7 pi over 4, right, is the same as 7 times 45 degrees, which is 315 degrees. I always like to think in degrees and then go to radians, just traditionally, but that's fine. Another possible one would be this. Another possible polar coordinate would be root 2 and negative pi over 4. Negative pi over 4 is negative 45 degrees. Okay, so that's what they're talking about in example 3. That's what they're talking about. Okay, are there any questions on that? Okay. Let's do a few examples here. Oh, I'm sorry. Let me upload my example. One moment. I think hold on one moment, class. Give me one moment. Okay, let me upload this. One thing I forgot to do, right? But we'll do it now. Just got to find it. It's here. There it is. Let's give it a moment here. while it's doing that, let me show you something else from the ebook while I'm at it. So you can have what are called polar equations. So in example 4, they say what curve is represented by the polar equation r equals 2. So now you're not dealing with function y as a function of x. You're dealing with the radius as a function of theta. R equals a function of theta. And if you have r equals 2, well, theta can be anything, but the radius is always 2. So you see, that would generate a circle, as you see there in figure 6, the pink circle. And a radius of 1 would generate that blue circle. And so basically circles, like for the circle with radius equals 4, okay, for that circle centered at the origin, the equation for r equals 4 would in Cartesian coordinates, that polar equation would be x squared plus y squared equals 16. That x squared plus y squared equals 16 represents a circle centered at the origin with radius 4. Okay, so you see what I'm trying to say. Let me mention it here. So if you have, this relates to example, well, let's go to example 4. Well, example 4, in figure 6 there, radius equals 4. Okay, so if you have x squared plus y squared equals 16, that's a circle centered at the origin with radius r equals 4, right? We know that. We know that. Well, if we wanted to convert that Cartesian equation to a polar equation, x squared plus y squared is r squared. So r squared equals 16, which means that r would equal 4. So you see, you have a Cartesian equation and then you have a polar equation. And polar, when you're dealing with circular figures, polar equations are more convenient to use. Okay, polar coordinates are more convenient to use. So a student told me one of the engineering courses he took, I think it was at Georgia Tech, all the problems they did were dealing with polar coordinates, like centripetal acceleration and so forth. So, it's important. It's important. So let me see here. Let's do an example or two here. Let me give you a moment to copy this example down, okay? Okay, so here we're given Cartesian coordinates, -1, √3, and we want to find polar coordinates. The first polar coordinate, we're requiring that r is positive, but theta is between 0 and 2 pi. The second polar coordinate, we're requiring that theta is between 0 and 2 pi, but r is less than 0. So the reason we have a restriction on the angle theta, and you'll see this in your homework as well, is because polar coordinates, there's an infinite number of polar coordinates for a point in the plane, an infinite number of representations. So what do you think would be very helpful to do this problem? What's usually very helpful in trigonometry to have? When you're doing a trig problem, what's always very helpful to have? I'll help you. Begins with a P. Seven-letter word. P-I-C-T. Oh my goodness. All right, Victoria got it. Thank you. Picture. I'd be worried if we couldn't get it with that. Yeah, picture. We've got to draw a picture. So next page, I'm going to draw the coordinate -1, √3. Now, √3, incidentally, is approximately what? About 1.732. Okay. All right. Well, let's see here. So in the picture, I got a nice picture here. Let me let you copy it down. Okay, so what I did here is I really used the picture to help, but I plot the point -1, √3, which I know is in the second quadrant right here. And I know that the radius is 2. And of course, 2 pi over 3 is 120 degrees. So you see, we have here a reference angle of 60 degrees. 60 degrees is pi over 3. So you get a 30, 60, 90 right triangle. And okay, so that's what you'd have to have. The let me just see here. One moment, class. Okay, sorry. Too many windows open here. Yeah. I mean, so one of the polar coordinates would be 2 and 2 pi over 3. that would be where the radius is positive. But if you wanted to have a negative radius, what you could do is you could go from 2 pi over 3 here and move out another 180 degrees, which equals 2 pi. No, pi, sorry. So you see, 2 pi over 3 plus pi is equal to 5 pi over 3. And if you look in the direction, of 5 pi over 3, which is 300 degrees, but you move backwards 2 units, that's going to get you to -1 root 3. So you see, it's like you look in the direction of 300 degrees, but you move backwards 2 units, and that'll get you to -1 root 3. So they have 2 polar coordinates here for A and B, and there's an infinite number of polar coordinates. Are there any questions on this particular problem? So in your homework for section H.1, which I will make available, there are problems where, for instance, they might want you to find polar coordinates for something like 1, -3. In other words, they give you a coordinate, an XY coordinate, that's not like a nice coordinate that you're used to. And then they want you to find polar coordinates for that. So I'm gonna, on Monday's class, I'm gonna do a problem like that. So if you choose to move ahead and work on the H.1 assignment, I mean, you can like not do like usually the WebAssign, it's these kind of problems, it's broken up into parts, and one of the parts might have 1, -3. So you just don't worry about that part yet, and on Monday I can discuss an example like that. Okay, I want to kind of stick to simple stuff right now. Are there any questions before I go back to the ebook? All right, well, let's go ahead and look at a few more examples here. From the ebook. Okay, so example 5 says sketch the polar curve theta equals 1. Okay, that's a polar curve. So that means that you're not told anything about the radius, but every point has to have an angle theta equals to 1. And 1, if you were to convert that into degrees, that, well, let me see. Hold on. I'll go to the whiteboard. One moment. We go to the whiteboard. What would 1? Well, yeah, we would use that. So that's right, Jonathan. So 1, remember, just means 1 radian. And we could take 1 radian and multiply it by 180 degrees divided by pi. And 180 degrees divided by pi is going to give you about 57.3 degrees, approximately. So that means that if you have a y x-axis, every point, and your equation, say, is theta equals 1. I mean, that's what we're looking at. Every point has to obey theta equals 1. Every point has to have, every polar coordinate has to have an angle of, like a point on the graph has to have a theta equal to 1 radian or 57 degrees. And so you see that's going to trace out, that's going to trace out a line. That's going to trace out a line. See that? And that's why example 5 is as you see it. See there? So example 5 in figures, you can see the graph in figure 7. Theta is always equal to 1. That's the second coordinate, and the radius is the first coordinate. So the radius changes 1, 2, 3, -1, -2, -3, but the angle theta always equals 1. Now there's another one I want to look at too. Let's look at something a little more interesting. Let's look at this example 6. Example 6, we have polar equation r equals 2 cosine theta. Okay, and we want to find the Cartesian equation for that curve. So 2 cosine theta, what you have to do, remember when you learned about functions of x, like y equals x squared, that's a simple parabola, right? When you learn how to graph those kind of functions, you would pick some good x values, find the y values for those x values, and plot the Cartesian coordinates. Okay, so like for y equals x squared, you might let x equal -2, -1, 0, 1, and 2, and then plot the corresponding y coordinates, or find the y coordinates and then plot the xy coordinates to graph out your parabola. It's no different with polar coordinates. If r equals 2 cosine theta, we have to find some good theta values. So those are the theta values that you standardly know in trig, from trigonometry: 0, pi over 6, pi over 4, pi over 3, pi over 2, all the nice angles, right? All the nice angles, multiples of 30 degrees, 60 degrees, or 45 degrees, or 90 degrees. So like in the picture to the right, they plot the coordinates. So like when theta is 0, radius is 2 times the cosine of 0, and that's 2. So you look at an angle of 0 degrees and move out a radius of 2, and so that gets you the point 20. Now if theta is 30 degrees, or pi over 6, well, 2 times the cosine of pi over 6 is 2 times the, let's see, 2 times root 3 over 2, that's root 3. And so your next polar coordinate on the picture there in figure 8 is √3 pi over 6. For pi over 4, the radius is √2, because 2 times the cosine of pi over 4 is 2 times √2 over 2. That's √2. And see, you keep plotting points, and what happens is when you're at pi over 2, okay, you're looking in the direction of 90 degrees, that's looking vertically up. Well, the radius is 0 there. And so you're just at the origin. But then when you get to 2 pi over 3, which is 120 degrees, the radius is equal to -1. Because 2 times the cosine of 2 pi over 3 is 2 times -0.5, and that's -1. And so you see how on the picture there they graph the polar coordinate -1, 2 pi over 3. So it's like you're looking in the direction of 120 degrees, but you walk backwards on a unit, a -1, a radius of -1. And if you plot all the points together, you trace out a circle. You trace out a circle. Okay, you trace out a circle. Now that circle is not centered at the origin. Okay, it's not centered at the origin. What would its equation be? Well, we can find the Cartesian equation quite simply. If we go to the whiteboard here, I mean, what you have, so this is kind of fun, right? Working with these polar coordinates. You have r equals 2 cosine of theta. That means r equals 2 times x over r, because cosine of theta is x over r. What I'm doing is I'm taking this equation in polar, this is a polar equation for that circle in example 6, and I'm going to come up with the corresponding Cartesian equation. Well, all right, so r equals 2x over r. I can multiply by r on both sides of the equation. And this is going to give me r squared equals 2x. But r squared, remember, is x squared plus y squared. So you have x squared plus y squared equals 2x. Okay. Let's try to separate it here. Well, then x squared minus 2x, x squared minus 2x plus y squared equals 0. And we can, how many remember completing the square? We're going to complete the square here. Hold on. Sorry, had to kill a little mosquito there. Don't like to do it, but you know. All right, so without going into detail, you can review completing the square. We would add 1 to both sides. And so this means we'd have x minus 1 squared, and then y squared is y minus 0 squared, and that equals 1. So you have a circle, center is 1, 0, and the radius is 1. Okay, and this agrees with, of course, the solution in example 6. So if we go back to the example then, if we go back to the example, I think we're good here. I think everything's good. Yeah. If we go back to the example, sure enough, that definitely looks like a circle of radius 1 centered at 1, 0. Centered at 1, 0. Okay, so this is really a nice review. And by the way, you can use Desmos to graph polar graphs. So r equals 2 cosine theta. I'll just show you this here. If we wanted to, let me see, if we wanted to do this graph in Desmos, let me see here, hold on, I have it. So the way Desmos works is if you're going to do polar graphs, you have to use an r and a theta. So on the left there, you have r equals 2 cosine theta. How many are seeing Desmos okay? Give me a thumbs up if you're seeing that on the left. Okay, thank you, Clea. So of course, you can adjust the picture, right? You can adjust the picture, but you see, and I'm sorry, let me just try to adjust it here. I might have to just, yeah, I'll have to do it this way. So you see, you get the polar graph. So there's a lot of things you can do with polar coordinates, a lot of things you can do. There's a lot of really cool graphs that you can do. I'll just mention this real quick. If we were to adjust this to r equals, say, let's say we had the cosine of 2 theta. How about that? How about that? How many are liking that? 4-leaf clover. That's a polar graph. R equals cosine 2 theta. How many like that? Give me a thumbs up if you like that. I know you have to like that. Right? All right. Yonatan's liking that. Clea's liking that. Susanna. Yeah, there you go. There you go. Okay, if are you comfortable? OPME likes that. So there's a lot of beauty coming up here with polar coordinates that we're going to learn next week. And we're also going to learn how to do integration with polar coordinates. Very important for your final exam. Very important. Okay, are there any questions before I stop the recording? Okay, I will stop the recording.